everyone, welcome to the next exercise on the static dial-right problem. In particular, we have to linearize the constraints, simply because non-linear constraints are pretty difficult to be solved by numerical solutions. We have some problems with that, so therefore every time when it's possible we should try to linearize non-linear terms, constraints, parts of objective function, and so on. So the question is now to use the big M method to modify the non-linear constraints. Okay, so you remember these are the parameters of the static dial-right problem. Okay, so this is what everything we have to know, and these are the decision variables. So with x saying 1 if and only if arc I to j is traversed by vehicle k, otherwise it's 0. Then uk is time at which vehicle k starts servicing vertex I, so either picking up the patient or delivering them. And w is the load of vehicle k upon leaving vertex I, so the number of patients inside the vehicle when they leave vertex I. And r is the ride time of the user I, so of the patient I. This is the pure time the patient is spending within the vehicle. Okay, so the objective function, we discussed that in the lecture, is the cost minimization. And now the question is which constraints are actually linear, and you can see, or non-linear, and you can see here that every time we have to multiply decision variables together, this is then non-linear. So in this case, this is the decision variable and this one. So the multiplication of both leads to a non-linear constraint, and the same also for the load constraints. So w is a decision variable and x is a decision variable, and therefore you have this non-linearity in this. When you check the other constraints, you see that everything else is fine. But as soon as you have some kind of product or division with several decision variables, you know that this is a non-linear constraint. Okay, and we now would like to get rid of this non-linearity because of the numerical issues that could arise. Okay, so let's start with the arrival time with the constraint group 5. So why do we talk about constraint group 5 and not constraint 5? This is simply because this one, this is this constraint, this inequality constraint, holds not only for one I, but for every I, j, and k. So that means you have several constraints, and this is why if you write things and if you look into the research papers, then you will see that constraints 5 ensure okay, or you can say constraint group. So as soon as this constraint should hold for several indices, then you can use plural and say constraints 5 or constraint group 5. Of course, if we talk with each other, then it's more simple to say simply constraint 5 is saying this and that. Okay, but if you write things down, you should watch out if this is a plural form, or if this holds only for one, then it's a pure single constraint. Okay, and what we also know is the domain of the decision variable. We know that this should be non-negative, and that means here that we cannot have a starting point which is negative. Okay, we will use that also later. So this one is simply the time at which vehicle K starts serving vertex J. So it's leaving at, let's say, 8, plus the service duration, so we need 15 minutes, so it's 8:15. This is the service duration, plus the time traveling from I to J, it's half an hour. So that means, so if this is 8 a.m., this takes 15 minutes, this takes 30 minutes. So you know then that you can only start at J at 8:45. Okay, so this is the earliest. This is the earliest point you are start serving vertex J. Okay, just as an example. Okay, and now we would like to linearize that, and what we know is these are the decision variables, and this is the decision variable. Okay, as soon as they have to be multiplied, this is a nonlinear constraint. Okay. Okay, now is the question, how can we linearize this constraint group? And what we can do is simply to check what if, so what if xij is 1? Okay, what does it mean for this constraint? That means the starting point at J for vehicle K is at least UIK, so starting point at I, plus the service duration at node I, plus the travel time between I and J. Okay, and if x, so here we should multiply it with x, and for the case that this is 1, that means we can delete that. So this is the case if we say that we would like to travel this particular path from node 2 to node 4, for instance, then this is our starting point at node J, which is 4. Yeah. Okay, if we don't want, if the solution is not using this path, then you simply multiply it with 0 the right hand side, and that means you have on the right hand side is 0. Okay, so this is the case if we want to, if we decide if we use this arc ij or not. Okay, and now the question is how to use this big M formulation to express this particular nonlinear constraint as a linearized version. So the idea is simply to say U jk is at least, and then having this the right hand side we had before, plus tij minus this big M formulation and multiplied by 1 minus xij. Okay, and this should hold for all ij in the vertex set and each vehicle k. Okay, so what does it mean? Now, what do we have now? If xij is now 1, everything is fine, right? So we have the left hand side is at least uik plus the service duration plus tij minus mij, and this is simply 1 minus, and now it's x is 1. Okay, so this entire term is 0, and we have exactly what we wanted before. Okay, so this is perfectly fine. So this constraint is said to be binding. Okay, so we have that as before, so everything is fine. And now if we don't choose this arc, if xij is 0, then we have our ujk is at least ui plus di plus tij minus m, and now it's 1 minus 0. Okay, so 1 minus 0 means we have here on that side minus some kind of capital, big M. Okay, and the question is now how to choose M, right? So what we could do is simply to choose a really huge number for M. Okay, so whatever, let's say 1000 or something like this. So that would mean we have here a uj that is somehow, you have here some kind of value minus a huge number. So that means you have some negative value on the right hand side, okay, which is fine, because what we also defined before is that our domain of the decision variable is anyway positive. So if we use a capital M formulation and we use some kind of huge value for M, then we have for this particular case a negative value. So this is an example for this case if we don't choose 0. So that means we would like to switch off, in some sense, to switch off this constraint, okay? So it's not binding. And it's fine if we choose a capital M, which is really huge, then we have negative value on the right hand side, because our domain of UK is anyway at least 0. We had that before, okay? And this is, so it means if it's at least 0, of course, then it's also at least some kind of negative value, okay? So everything is fine. But the question is, our question was, so here you see the nice picture of it. The task is how to choose the smallest M, okay? Because sometimes, although it's theoretically valuable and everything's fine, for the algorithm, the algorithm itself could lead some kind and run into some kind of problems and issues because of this huge number. Okay, so we have some kind of numerical issues if we choose M that is too large, and therefore every time we would like to restrict M to the smallest value so that we have a robust algorithm at the end. Okay, so the question is how to choose that. What we also know is that our uj has to be inside this time window. Okay, so between the earliest time that the service should start and the latest point L. Okay, this is the constraint group 9 in our formulation. This has to be assured. Okay, so M should be chosen in such a way that it still ensures that we do not interfere with this time window. Okay, so which means we know that our uj should be at least ej, and of course this should be at least the right hand side we had before, plus d, the service duration, plus the traveling time, minus this big Mij. And this part is already fulfilled by the time windows in constraint group 9. Okay, so this is fine. Now we want to check the right side so that Ij is still fulfilled. So Ij should be at least this right hand side, plus Tij minus M. And here we know that if we bring that to the left hand side, we know that our capital or big M should be at least ui plus di plus t, and then we bring the earliest possible time to the right hand side, so minus ej. Okay, so this is what M should look like. This should be the lower bound, but the problem is that we have still this u in the formulation. Okay, this is the decision variable UK. The decision variable is still within the lower bound of M. So if you remember, at the end we should multiply M with X. So that means if M contains again a decision variable, we would have again a nonlinear constraint. Okay, and this is what we want to avoid. So we don't want to have M depending on some kind of a decision variable. But what we can use here, we know that U, so we know basically the upper bound. So we know that UJK is cannot be later than the latest allowable time from our time window. So this is LJ. So we know that we have an upper bound of U, and we can simply now replace that in our formulation so that our big M is now this lowest or latest time we can serve J instead of U. So we replace the decision variable by its upper bound, and everything else remains the same. I'm sorry. That should be where's my, yeah, that should be I, which is fine because it doesn't matter if we have IJ, but here in this formulation, here we have we use I instead of J. Okay, so this is the latest time we can start with serving node I plus the duration at node I plus the time traveling from I to J minus our earliest possible service time at J. Okay, and with this we can now linearize that. We plug in this formulation into our constraint group and our now linearized constraint group with this formulation, and then we are sure that our U stays within still this time window. Okay, the next one, so again you can see it here. If you need a nice handwriting, then you can check that one. So in the second constraint group that was nonlinear is then vehicle load. So this is the constraint group 6. That was the W, so the number of patients I pick up at J node in vehicle K, and this should be the number of patients I have picked up at I, the same for the same vehicle, plus the Q, the number of patients I pick up at node J. Okay, and this is multiplied again by Xij. So if we travel this particular path from I to J, then we also have to adhere to this particular constraint group. So again, this is for every I and J in the vertex set, and K is the set of vehicles. Okay, so the question is now how to linearize this constraint group. So it's basically the same as before. So what we have done in the previous task is also just copied here. Okay, it's again Wi K plus Q J, and then minus capital M, but we used it already, so let's use another capital letter Wij, and the same idea as before. Okay, and the same question as before, how to choose now the smallest W. So what should W look like? How should it look like to be as small as possible? So what we know is we have this constraint group 11 saying that the load Wik should be at least the maximum of 0 and q, and not more than the minimum of the maximal capacity of this vehicle, or the maximum plus qi. Okay, maybe an example would help here. Okay, assume I is a pickup node with, let's say, 3 patients. Okay, so QI is, we have to pick up 3 patients at QI, node I, sorry. So that means for this constraint group that this is the maximum of either we have no one that we should pick up, or 3. Okay, obviously this is a 3. Or, and this is the maximum load we can take within our vehicle. It's the minimum of, let's say we have, the vehicle can carry not more than 5 patients. And here we have places for 5 patients, and then we should pick up 3 more. Of course, we take the minimum of it, which is 5. Okay, so if we are leaving node I, we can only have a load of patients between 3 and 5 patients. Not more. We cannot have more in our vehicle. Okay, either 3 or up to 5 patients. The other way around, if QI is a delivery node, okay, and we drop off 3 patients at node I, then we would have here a minus. That would mean this here is 0, so we would deliver 3 patients, we have less, so Q is a negative value, and here we have then not plus but minus 3, and that would mean the minimum so that means we take 2. So that means the load of vehicle K leaving node I, if it's a delivery node, then it's between 0 and 2 patients. Okay, not more, not less. Okay, so this is the example for this particular constraint. And now let's go back, because we would like to linearize that. So what we have again is here the max between of 0 and Q. J is at least, okay, this W I plus patients we pick up at J minus this big W IJK. Okay, and if we bring that to the other side, then obviously we have this big W should be at least our right hand side plus Q J minus, and then we should use the lower bound of the 11th constraint to put it on the right hand side, which is the maximum of 0 and Q J. Okay, the same problem arises as before. W again is a decision variable, and that means if our big W contains a decision variable, we would again, so you can see here, if we plug in this one into this expression, we have to multiply that by this decision variable again. And that means we haven't linearized this constraint group. Okay, so we have to get rid of this W in the formulation, and we can use the same trick as before. And I need some space here. So we use the same trick as before. We know that W has an upper bound. Okay, we cannot carry more than the minimum of the capacity, overall capacity Q k plus qi. Okay, so we know this is our upper bound, and now we can use that and by replacing this w. So we have w, our capital W is then the minimum, so we replace that, the decision variable, by this upper bound as before when we talked about the arrival time, plus qj plus qj minus the maximum of 0 and qj. Okay. Okay, so this could be it, but what we can also do is to simplify that even further. So first of all, I would like to show you the nicely written one. Okay, and now we would like to simplify this expression even further. Okay, so we ended up using this determination of w, but we can also simplify that further. So what is shown here is that if q is positive, if q is positive, that means if this is a pick-up node, then we pick up patients. So that would mean that qj minus the maximum of 0 and qj is exactly 0. Okay, because if this is positive, if there's some kind of positive value, this is q. And maybe to be very clean, if this is a positive, a real positive value, then it is qj, and then this entire second and third part would cancel out. Okay, then we would have 0. If it is negative, okay, then we have qj minus the maximum of 0 and qj. So that would mean we have the maximum over here, and we would have some kind of so that means we have here a negative value, here we have 0, that means we have something negative on the side. Okay, and what we are doing now is simply to take the bigger part, so we replace capital I j k by simply using only the minimum, only using the upper bound of qk and qk plus the load of node I, node j. Okay. So we simply simplify this by cancelling the last parts out, because what we have here is, what is really important is to adhere to this lower bound. Okay, this is what is binding, and this we have to assure that this w is not violating it. Okay, that we still have this lower bound. Okay, but on the other hand, the upper bound can be higher because it's then not binding. It's similarly I explained that with, if it's 0 and the u it was 0, the arrival time was at least 0, and if we have another constraint saying that u is some kind of negative number, that doesn't violate that, because the non-negativity constraint is the binding one. This is similarly here, so that we choose w so that this lower bound is fulfilled. Okay, and that's it. If you have any questions, see you in the Q&A session. Thank you very much.